Good morning, everybody, and welcome back to Next Door NetAdmin. We're back in the same place as usual. Pardon the interruption last week while I was on the road. But before I left, we were last talking about the 7 layers of the OSI networking stack. And the last thing I talked about was about some of the lower levels in the stack, specifically layer 1, where we had hubs and repeaters, layer 2, where we had bridges and switches. Today, I'm going to talk a little bit about layer 3, where we find routers. There's a lot to talk about in the world of routing, but specifically what I'm going to be talking about today is just the basics, is how do routers know where to send your traffic? How do they figure out where to send it? How does this whole process work? Okay, so the first thing that I will mention is the exception to the rule, and then we'll get on to the rule where 99.995% of your traffic will actually be handled. The exception here is something called IP source route. Technically speaking, there's an option in IP that allows the sender to specify the route they want their traffic to take. And any network admin worth his salt will disable that option on their routers completely. Why? What's the problem with letting the sender tell you what path he wants his own traffic to take? The problem with that is, what if it's not the sender who set that option? What if it is some malware on the PC that says, oh, I see that you're wanting to log into Facebook. Tell you what, why don't I let your browser say that you're talking to Facebook, but I will just quietly redirect your traffic to go through my attacker server first, and then it will continue on to Facebook, just so that I can kind of be a man in the middle and read the traffic that you're sending. And as a part of that, they might also strip away the SSL so that there's no security on that. That used to be a big thing. So for security reasons, most network admins will disable IP source routing as an option. If it is set, the router will ignore it, and it will just go on and do its standard routing algorithm. So, that being covered, let's get on to the actual normal routing algorithm, and we'll talk about that, because this is where almost all of your traffic is going to be processed. One of the first things to understand about routing is that all routing decisions are local. Period. The router may get information from other routers on the network, but it cannot use information that only another device knows. So if it's not told that a network is over on this other section serviced by this other router, then it doesn't know about it. All routing decisions are local. If you get a packet that is destined for some network and you don't know where to send it, you drop it. You don't route it anywhere at all. Period. That's just the way it goes. This could lead to problems, yeah? Because how do you expect every router on the network, on the entire internet for that matter, to know where every single address should go? So there are some rules that we can use to kind of tell routers, hey, this is where things should go. Some of the rules might be redundant. If you've looked at IP addresses, you know that along with the IP address, there's usually a subnet mask. And getting into subnetting is a discussion all on its own, so I'm not going to cover all the ins and outs of subnetting today. But the most important thing to know is the longer the mask, the more specific the route. It's a little bit, if you think about street addresses for the moment, I can tell you what city I live in. That is still going to be kind of difficult to find me. If I tell you what street I'm on, as well as the city, that's a little easier. If I go all the way down to the house number I am at, plus the street, plus the city, now that is the most specific version of an address, of a location. So the longer the subnet mask, the more information you have and the more specific the route. A router will always use the most specific route first, period. If you can say, I know about this specific route and I know about this general route over here, I'm going to use the specific route first. This is what allows us to put in a default route. If you set up a router with just a default gateway or a default route, it'll say, this is the least specific route of all. It's actually got a length of 0. That's how non-specific this is. So if I have literally no other place to send this traffic, I can send it to the default route. Then and only then can I send it to the default route. If you have any information that is more specific, use that first. How does it get these more specific routes? How does it know about these more specific networks? Well, first of all, it knows what it's actually connected to. And so it'll know the subnet mask of what it's already connected to. And that goes into its internal routing table. If it is running a dynamic routing protocol, and there are many of these, some of the more common ones are like RIP, OSPF, EIGRP, BGP, ISIS. If it's running a dynamic routing protocol, it may be receiving information from other routers on the internet or on the local network that tell it, I have a specific route for this network over here. You can send it through this router to get there. Cool. If it has that information locally, then the router will act on it, but it has to know about it locally. If it doesn't know about it locally, it can't use it. And conversely, if configured to do so, the router will also advertise to other routers in the network, hey, I am locally connected to networks A, B, and C. If you want to send something to networks A, B, and C, you can send it through me, and I will forward it accordingly. That works as well. You can also configure the different routing protocols to talk to each other, or what is called route redistribution. So if you get a bunch of routes through, say, OSPF, cool, they're pointing elsewhere, you can redistribute that into something like BGP and advertise that elsewhere. It's possible. And the exact process of doing so is fairly advanced. And for most network admins, you're never going to need to touch that. If you're on the small to medium business level, if you're on the home level, all you really need is your default route, your default gateway. The router knows what it's directly connected to. That's all it's responsible for. Everything else can just go out the default gateway to your ISP, and it's good. You really only need to worry about more than that in larger networks. And of course, I've left out the thing that most network admins will use in a medium to large network up to a certain size, and that is static routes. You, the network admin, are perfectly capable of telling the router, hey, I, the human, know about a route that you can get to through this router over there. If you want to reach that network, just send it over there. And that's perfectly valid. But you have to remember to program that in. And anytime it changes, you have to go back and change that programming yourself. It will not automatically update. For most small to medium enterprise networks, this is sufficient. Most of them will only have one router anyway. And if you only have one router, there's no need to do any static anything and no dynamic anything because everything connects directly to the router. But if you have something like a VPN gateway that isn't on the router, you might need a route to tell the router, hey, if you're sending something to somebody on the VPN, don't send it straight out to the internet. Send it over to the VPN gateway first. And then it'll go in the right direction. If you have multiple routers for redundancy, say, and they're connected to a different set of networks, then you might also say, hey, if you want to send something that's actually on the other side of the network, that's handled by the other router, you need to send it via the other router. Don't send it just straight out to the internet because it's never going to get to where it needs to go. And in a small to medium-sized network, you can get away with that because that kind of setup, that kind of structure is not likely to change very often. In much larger networks, think of a network on the size of Microsoft or Amazon. Something where you have hundreds of buildings, hundreds of routers in this internal network. And there's probably a fair degree of interconnection for redundancy. It's not just a single link between each building because that would be nuts. That would be so unreliable. In that case, you're going to move to one of the dynamic routing protocols. So it can say, okay, I have two ways of getting to this particular network. One is a single hop. It's just a single link to traverse. And the other one takes me through 3 hops. It takes me through 2 other routers before I can get to the network because it has a bit more of a loop to travel for redundancy's sake. Under normal circumstances, you want the router to say, well, I'm going to choose the shortest distance, the lowest hop count. That's just what I want to do. But if that link goes down and the router stops hearing the advertisement through that shorter distance, it still has a route to the network. It just sends it on a longer journey because the shorter path is down for whatever reason. Whether that's an internet trouble or somebody dug through the line or somebody goofed up a set of configuration and the equipment's not talking to you anymore, or it's down for maintenance or anything else like that. Having multiple routes to a destination is a good thing, but only one will ever show up in your routing table. The others are candidate routes, and the router's only going to look at the actual routes that are in the routing table if it needs to send traffic to that destination. And then if that route goes away, then it has substitutes that it can just promote into the routing table and we keep going. Then there's the concept of administrative distance. Administrative distance can be considered to be a measure of how much do I trust the source of this routing information. If the network is directly connected, that usually has an administrative distance of 0. That is the most reliable information you can have. The router actually has an address on this network. It's directly connected. It's just there. 100% true, reliable. It's there. Statically configured routes that are inserted by the administrator will typically have a very low administrative distance. On a Cisco device, by default, it has a distance of 1. I think on a Fortinet device, by default, it has an administrative distance of, I want to say either 5 or 10, and I'm not 100% sure which, but it's still fairly low. A route that you get from DHCP that is just dynamically configured will typically have a very high administrative distance. It is considered very unreliable. Again, on a Cisco device, that has an administrative distance of 254, and the maximum is 255. So if you have a default route assigned through DHCP, that is what you want to trust the least. Because if you're getting an administratively configured default, you want to trust that. If you have something that's directly connected, you want to trust that. If you have information that's been delivered through other dynamic routing protocols, you might trust OSPF more than you trust RIP, which is pretty standard actually, because they're different classes of routing protocols. OSPF is a link distance protocol that actually figures out the shortest distance in the network, whereas RIP is just a pure hop count metric. How many other devices does it pass through? Which may not actually be an accurate way of looking at it. If you go through two routers running at 100 gigabit a second versus one router running at 1 megabit per second, sure, RIP will say, well, there's two routers there, it's a longer distance. But a network distance view will often go, hey, that's 200 gigabit links. That's going to be way faster than a single 1 megabit link. I should prioritize this one, even though technically it's more routers to go through. So because of that, OSPF and other link distance routing protocols will typically have a lower administrative distance, making them more reliable for a given route than a pure hop count protocol. But what I said before still applies. The most specific route wins. So if I have a very specific route, say to a /28, that is delivered to me by RIP, and then I have a less specific route, say a /24, that is delivered by OSPF, OSPF is, generally speaking, going to have the lower administrative distance, but the route from RIP has the more specific route, and so I'll use that route first. Administrative distance really only comes into play if you have two routes that have the same specificity. Okay, if they have the same specificity, they're both /24 networks, which one do I prioritize first? The first thing to prioritize is the one that's directly connected. That is always believable. The second one to prioritize is the one that the admin has configured, because if you're not going to trust your admin, what good are you? Speaking as a machine. And then you go through the different protocols in their reliability. And then the last one, the lowest one on the totem pole, is DHCP. If nothing else, I suppose I can use the default gateway that's advertised by DHCP. No idea if it works or not, but it's worth a go in the end. So there's a lot of complexity that goes into figuring out where the traffic actually goes. And like I said, all routing decisions are local. All of them. Which means if you have multiple routers in the path, one router may say, oh, to reach this network, I send to you. And if the other router says, oh, well, to reach that network, I send it over here, now you've got a problem. The traffic's not going anywhere. It's just going in a loop back and forth between the routers. It will eventually figure that out, and the packet will just die, having not been sent anywhere. And the sender will hopefully receive a TTL time expired, which is the time to live. If it reaches 0, then the packet is considered unroutable and it just gets killed. But when you have a routing loop like that, neither one of these devices know about it if they were set up statically. And that's why static routes are feasible for smaller networks where an admin has insight into everything, but not at all for larger networks, particularly as links go up and down, equipment is taken in and out of service. It's a little crazy. So for an admin, if you're troubleshooting through several routers where each packet is going, you cannot simply rely on, well, it's going to the internet. You cannot rely on that. For a network admin to be able to correctly trace the path, you need to go through every router along the path and say, what's your routing table? What's the administrative distance? What's the network mask that you've assigned to this route? How specific is it? And you have to understand how the router will prioritize that before it figures out where it's going to send that traffic. And then you also have to consider, how does it know where to send the reply? Because that got the packet to its destination, great, but how does the destination send back to the source? Again, you have to go through every routing table along the way, but now you need to look for, do you know how to send traffic back? Because communication is a loop. You can have one-way communication, but then it's just going to look like, I never reached the destination because I never got a response. Maybe you did reach the destination, and it's the response that has the problem. So a network admin has to look at the entire loop of traffic, and that often means going through every single device along the way and assessing every single device and going, does this make sense? If it doesn't make sense, how do I fix it so that it does make sense? And if it does make sense and you've verified the entire layer 3 path, which you can easily test by just running ping, like I said, because ICMP runs at layer 3. If you verified your layer 3 is good and you've got communication forward and back, then you need to look at a higher layer, because a layer 3 check will make sure that layer 2 and layer 1 are also working as part of that. And so, cool. If you can't ping, but your layer 2 looks good, then you're looking at routing tables and figuring that stuff out. And once that's resolved, if it's still not working, you're looking at a higher level, whether it's TCP or the protocol or everything else higher in the stack, which we're not going to go into today because for one day, I've rattled on long enough. So hope you found that interesting. Thank you very much for watching. I am your next door net admin, and we'll see you next time.